Okay. So next is your momentum coefficient, that is beta. Okay. So momentum we know mass into velocity. Okay. So in we have already discussed how you are going to find out mass. Okay. So we have to find out mass, then we have to multiply it by velocity. You will get momentum. So it's this momentum derivation is similar to your alpha derivation. Okay, this is your level of water. We consider a small elementary area, and then we find out momentum. Okay. Okay, in energy coefficient, we have considered kinetic energy. Okay, we have derive an expression for kinetic energy for that particular small elementary area, and then we have taken summation. Okay, for alpha, that is your energy coefficient. Then name itself we can identify here, it is momentum coefficient, that is why we have taken momentum. Okay, and in energy coefficient, that energy term, that is why we have taken kinetic energy. Okay, and in velocity, average velocity, we have considered discharge, and the process is same for all the three. Okay, we have to consider a small elementary area. The area of that particular is dA. Okay, and then total cross sectional area is capital A, and this is dy. Okay. Okay, so we have to calculate again mass. Okay, mass is equal to weight by gravity, we have already discussed. Okay, mass is equal to weight by gravity, and in place of weight we can write specific weight multiplied by, as we are calculating mass for that particular small area or elementary area, so that area will be del A or dA, it's up to you what you want to write. Okay, multiplied by velocity. Okay, velocity. Okay, divided by g. This is give you mass. Okay, so here there is some error. Okay, this will this square will be not there. Okay, so don't confuse, it will be del A into V. Okay, then this is mass multiplied by velocity, you will get momentum. Okay, so mass into velocity, you will get momentum, then it will become V square. Okay, so for total momentum for the whole cross sectional area, we will take again summation or integration, whose limit will be from 0 to y naught. Okay, we have already discussed. Okay, so we will take summation or integration. Okay, so you consider this is at equation 1. Now we are taking the whole cross sectional area, and we are going to take the momentum for the whole cross sectional area. Okay, again it is mass into velocity, so mass, if we consider the whole cross sectional area, it will be specific weight multiplied by total cross sectional area multiplied by capital V. Okay, divided by acceleration due to gravity. Okay, and this velocity, because of this velocity we will multiply by a coefficient called beta. Okay, our aim is to find the expression for this beta. Okay, so this is area into velocity, so that's why they have written q. Okay, we know q equal to area into velocity, so that is why they have written q. You can write area into velocity also. Again they have replace that q by area into velocity, so you better you write area into velocity. Okay, don't write q. Okay, so this is mass, again it will be a velocity, so mass into velocity for momentum. Okay, so then we are going to equate both the equation. We're going to equate both the equation. And again, you see specific weight by gravity. Here also specific weight by acceleration due to gravity. These two will be cancelled out. Okay. Then what will be left out is del A into V square. Here also area into velocity into V. Okay. Or you can say area into V square. So if you find out beta, we are replacing summation by integration. Okay. This area is there, capital A. So 1 by A. This is V square and this is small also V square. So small v by capital V whole square, and then del A is left out. Okay. So this is the general expression for beta. Okay. Irrespective of any shape of the channel. Okay. Now, for example, if we consider a rectangular channel, so these things we have already discussed. For rectangular channel, your area for small element in area is b into dy, whereas the cross-sectional area or capital A is b into y naught. Y naught is the maximum depth of flow for that particular rectangular channel. Okay. So beta again integration, the limit will be from 0 to y naught. In place of area capital A, we have replaced by b into y naught. Okay. Small v by capital V whole square. In place of del A or dA, we have replaced by b into dy. Okay. So 1 by y naught, this b will be cancelled out. The width of the channel, this b and this b will be cancelled out. So what will be left out is small v by capital V whole square dy. Okay. See here also we have average velocity v. So whenever you are going to ask to find out alpha and beta, or you can say energy coefficient and momentum coefficient for a particular channel section, first we have to find out the average velocity. Okay. Then we are going to substitute those values in alpha and beta, and we find out this result for alpha and beta for the particular channel. Okay. I'll give you 1 minute. You just be ready with a pen and paper. Okay. Next, we are going to solve few problems related to this alpha, beta, and average velocity. Okay. I'll give you 1 or 2 minutes. You just be ready with a pen and paper. Okay, if you don't have any doubts, then we will continue with solving few numericals related to your energy coefficient, momentum coefficient, and average velocity. Okay, so here is our first question, that velocity distribution in a rectangular channel of width of the channel is given b. Okay, depth of flow, that is your maximum depth, is given y naught, and for the small v, velocity for that particular small element in the area is given one expression, that k root over y. Okay, where k is a constant. Okay, so we have to calculate the average velocity, alpha and beta of the channel. Okay, yeah. So you try to solve, as average velocity equation we have already derived and we have already discussed. First we need to find out the average velocity, then only we can find out alpha and beta. Okay, so this is the expression for rectangular channel, average velocity for rectangular channel. So here 1 by y naught, the limit is 0 to y naught. In place of small v, we have a expression, it's already given, that is k multiplied by y to the power half, or you can say root y. Okay, but here we are going to consider as y to the power half. Okay, then you integrate. Okay, so k will be, you bring it out. So k you bring it out, as k is a constant. So k by y naught, then if have to integrate y to the power half. If you integrate y to the power half, if you integrate y to the power half, it will be y to the power half plus 1 divided by half plus 1. Okay, so what will be? It will be y to the power, it's 3 by 2 divided by 3 by 2. Okay, so again if you bring it out, it will be 2 by 3, 2 by 3, y to the power 3 by 2. Okay, then we will be having limit, that is 0 to y naught. Okay, that's what they have did. Okay, k is constant. Now, Mahajan, you want to ask me something? Okay, 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 no problem. Okay, okay. So what we have to, this is a simple integration. Okay, so we have one by y naught integration. We have limit from 0 to y naught. Okay, k y to the power half. That is small v. Ah yes, it's a simple integration. In place of small v, that expression is already given. That is k into root over y. Okay, so in place of root over y, we have considered y to the power half. Okay, and we substitute in place of small v. Okay, so here integration of y to the power half will be your y to the power half plus 1 divided by half plus 1. Okay, so this half plus 1 is 3 by 2, so y to the power 3 by 2 divided by 3 by 2. Okay, if you bring it out, that's 3 by 2, 2 will go up. Okay, so it is 2 by 3, y to the power 3 by 2, and then we have limit. Okay, don't forget, we have a limit from 0 to y naught. Okay, so if this you solve, that 2 by 3 will be there, 2 by 3 will be there. If you substitute the limit, that maximum limit is y naught, so y naught to the power 3 by 2 minus max minimum limit is 0, 0 to the power 3 by 2. Okay, so that ultimate result you are going to get is 2 by 3 multiplied by y naught to the power 3 by 2. Okay, so and this is we have already a by y naught. Okay, it's already there. Okay, after integration we are going to get 2 by 3 y naught to the power 3 by 2. Okay, after integration of this, but we have taken out the k by y naught as it is a constant. So if you further solve, this k will be there, 2 by 3, k is a constant. Okay, y naught 3 by 2 divided by y naught. Okay, so it will be y naught to the power half. Okay, so this is the answer for your average velocity. Okay, that is 2 by 3 k y naught to the power half. Okay, so you what you do one thing, you try to solve for alpha. Okay, you use that alpha equation, use the alpha equation for rectangular channel. Okay, and you try to find out alpha. Okay, it will be around 1.35, and if you find any problem, then you can discuss here. Okay, so what you do, you just try to first you try to find out that alpha value. If you find any difficulties, just let me know. Okay, alpha equation you always remember 1 by y naught integration 0 to y naught small v by capital V whole cube dy. Okay, for rectangular channel. We're getting the value that the alpha is 1.35. Those who have completed, you try to find out beta. Okay, this is 1.125. Okay, this value will be 1.125. Okay, one. Okay, this is 1.125. That one is missing. 1.12. Okay, first you find out the alpha value. It's very simple. Like previous one, we have to substitute the small v. Okay, and in place of capital V, we have already derived that expression, that 2 by 3 k y naught to the power half. Okay, so if you see here, what small v we know, k into y to the power half whole cube divided by, in place of capital V, we substitute the average velocity expression that we have obtained. Okay, that is 2 by 3 k y naught to the power half. So this k and this k will be cancelled out. Okay, then you do the integration part. Okay, that this is your y and this is y naught. Y naught is your constant, so you bring it out. 1 by y naught is already there. Okay, so multiplied by 1 by y naught to the power half, and then you have cube also. Okay, so here it will be cube. Okay, then there will be integration, and what will be left out? 2 by 3 also your constant, so you bring it out. 2 by 3 multiplied by 1 by y naught is already there, multiplied by 1 by y naught to the power half, and then you have cube. Okay, so what will be left out? K is already cancelled. You have y to the power half to the power cube. Okay, integration, that is 0 to y naught. Okay, then you do the integration, and you see, you find out you are going to get this value 1.35. So we are going to move on to the next numerical, okay? Or if you have any problem, then we can discuss now, okay? If you find out any difficulties, calculate these values, then we can discuss, okay? Otherwise, we can move on to the next numerical. Okay. Next numerical is your the velocity distribution. Again, it's in rectangular channel. Depth is given 2 meter. Okay. And for small v, the expression is given. That is y by y naught. Y naught is nothing but that 2 meter. Y naught is given. Okay. Y naught is equal to 2 meter. Y by y naught to the power half. Okay. So find alpha and beta. So definitely to find out alpha and beta, first we have to find out the average velocity. Okay. To find out average velocity, again we are going to use the expression for rectangular channel for average velocity. Okay. We are directly using rectangular channel expression, as here it is given rectangular channel. Okay. So for average velocity, again it is a y by y naught integration from 0 to y naught, that is a maximum limit, and then small v dy. In place of small v, we are going to substitute this equation, that is y by y naught to the power half. Okay, dy. So similarly, you can find out the y v value. Okay, that y naught value is given 2 meters, so that is why 1 by 2. Then your integration limit from 0 to 2, y by, again in place of y naught we have substitute 2 to the power half dy. Okay, if we further solve, 1 by 2 multiplied by, this is again we have constant, that is 1 by 2, and then we have half, so 2 to the power half. Okay, what will be left out? Integration of y to the power half. Okay, so you all know integration of this will be 1 by 2 to the power 3 by 2, I think. Okay, that is 3 by 2, 3 by 2 multiplied by, now we have to do the integration, that is y to the power half. Okay, so y to the power half, half plus 1 divided by half plus 1. Okay, so you further calculate, you will get this value. Okay, so 1 by 2 to the power 3 by 2 multiplied by, so it will be again 3 by 2, it will be 2 by 3. Okay, 2 by 3 multiplied by y to the power 3 by 2, then we have limit 0 to 2. 2 is the maximum one. So okay, if you are going to solve again, 1 by 2 to the power 3 by 2 multiplied by, we have 2 by 3, this 2 by 3 multiplied by, we have to first substitute the maximum limit, that is 2. So y, in place of y, we have to substitute 2, 3 by 2, okay, minus, then 0 to the power 3 by 2 is 0, okay. So this 2 by 3 and this 2 by 3 will be cancelled out. What is left out is 2 by 3. So that is why your V is 2 by 3 meter per second. So similarly, you find out the alpha value, okay. For alpha value also, you have to replace that small v by that expression that is given, y by y naught to the power half, okay. And capital V we have to replace by 2 by 3 that we have already calculated, okay. Alpha value you are going to get is 1.35. And beta value you are going to get 1.125, okay. So for alpha, it will cube. Always remember when you talk about alpha, it's cube, whole cube, and for beta, it's whole square. Okay. So in the next class, we are going to solve few more questions related to your energy coefficient, momentum coefficient, and your average velocity. And then we move on to your next section, that is your uniform flow. Okay. And I suggest all of you to solve few numericals of your own. Okay, just for practice, because in the examination you are not getting much time. Okay, so you should know how to integrate. So it's better if you solve more and more numericals. Next, one derivation is there. Not derivation, it's just so that we will solve some new problems from our exercise. Okay, those are a little bit easy. These are solved exercise. We are going to solve from the exercise, and for those you have to bring your pen and paper. Okay, because those solutions are not there. Okay, so the next class we solve few numericals from there, and then we will move on to the next section, that is your uniform flow. Okay, thank you.